them before the end of today and email you your mark, your feedback, and your the full solutions. So check your email later today. You should get an email from me. If not today, you should get it tomorrow, right? Because I got no teaching assistant helping me. I need to do all the marking and inputting all the marks and writing feedback. Everything I have to do myself. So I got no teaching assistants. So give me some time. You will get it either today or tomorrow. Okay. All right. Now, before I start, one of you guys asked me about the L'Hopital's rule. All right. So let me do some examples on. So this is example 1. So suppose you have sine of x divided by x, taking the limit as x goes to 0. Now you know that sine of 0 is 0, and so you have 0 divided by 0, which is a case you can use L'Hopital's rule. So if you use the L'Hopital's rule, the derivative of sine of x is cos of x, and the derivative of x is 1. So this becomes cos of 0, which is 1. All right, so this is don't worry, I don't have COVID, but I just have a bad cough. Okay. Another example is the limit of ln of x divided by x as x approaches 0. Or rather, let's say x approaches infinity, right? Now log of infinity is infinity, and x is also infinity. So you have infinity divided by infinity, right? So again, you can use the L'Hopital's rule. So you should differentiate the top and the bottom. So the derivative of ln x is 1 over x. The derivative of x is 1. Alright, so this becomes 1 divided by infinity, which is 0. Alright guys, so these are 2 examples on the use of L'Hopital's rule. Okay. If you want more, I can do it later maybe. I hope you're okay, right? So let's return to the class now. So this week I asked you guys to watch 4 videos. I hope all of you have watched the 4 videos. So the first video is on conditions to check if the extremal types theorem holds or not. Remember, we talked about the extremal types theorem last week, right? And in order to check if it holds or not, you need to check 3 conditions. Condition for type 1, type 2, and type 3. And that can be really time consuming. I mean, you guys have been doing the quiz 1, you know how much time it takes to check each of the conditions. Now, so is there like one condition you can check to see if any of the conditions holds or not? And fortunately there is, but it's only, you can apply this condition only for a discrete random variable. So if x is a discrete random variable, and the limit of this is 0, then the extremal types theorem will hold. So in other words, if the limit is 0, then one of the three conditions, type 1, type 2, or type 3, must be satisfied. And if the limit is not 0, then none of the three conditions will be satisfied. Okay. All right, guys. So these are, I did some examples on those. This is, I hope you looked, this is example 1 on the use of the condition, where it turns out that the limit is not 0. So the ETT fails to hold. Sorry, you can't see it. ETT fails to hold, right? And this is the second example I did. You have binomial, and again the limit is 1, which is not 0, so again the ETT fails to hold, right? This is the third example, is discrete uniform. Again the limit is 1, which is different from 0, and hence the ETT fails to hold. Alright, so that's the first video I asked you guys to watch. Now the second video I asked you guys to watch is about definition 1 of extreme value. Remember last week we looked at the distribution of the extreme value under definition 1, and we found out there are 3 possible limits: the Gumpel, the Frechet, or the Weibel. Now for a practitioner, somebody who's not a mathematician, like somebody from agriculture or environmental sciences, who does have no background in mathematics, he will not be able to go and check which of the 3 conditions will be satisfied, right? So you need to have like is there a formula that you can use that combines the 3 limits, limiting distributions, the Gumpel, the Frechet, and the Weibel, into one formula? So instead of having to check those 3 conditions, the question is this: can the 3 limits can be combined into one, right? So that for a practitioner, he doesn't need to bother about checking the conditions, right? And so he just assumes that the extremal types theorem holds, and then uses the formula that combines the 3 into one, right? And fortunately there is a formula, and that formula is known as the GEV distribution. GEV stands for generalized extreme value, right? And this is the CDF of the GEV distribution. It has 3 parameters: the shape parameter, scale, and the location parameter. And this is the notation for a GEV random variable. And so this formula combines the 3 limits into one. And before I talk about why that's the case, let's look at the domain. The shape parameter psi, the shape can take any real number, minus to plus infinity. So if psi is positive, then the domain for x must be this. If psi is 0, the domain must be this. And if psi is positive, the domain of x must be this. I hope you followed this. I mean, if you did not follow anything in the video, then please let me know. I will go through over again, okay, before. And so therefore the domain of x being the GEV random variable, is one of these depending on the sign of the shape parameter. Now in the next slide, how to combine, or how come the GEV distribution? Yes, sir.
What about the other 2 parameters? Are they not affecting the domain of
No, it's only the shape parameter fx, not the location or the scale. No. Yeah, that's a good question. Yeah, thank you. All right. Now, next question is how I said a second ago that the GEV distribution combines the three limits into one formula. Now, what's the explanation for that? The explanation is given here, that when psi is negative, it turns out that this formula reduces to this formula here, which is of the same type as remember, this is the formula for the CDF of the viable distribution, which is one of the limits, right? Right? And when psi is positive, right, it turns out that this formula reduces to this formula here, which is of the same type as this, and this is the Frechet limit that we talked about last week. And when psi is 0, right, it turns out that this formula here reduces to something like this, right? Right, which is of the same type as this, and this is the Gumpel limit that we talked about last week. So hence, we have shown that the Gumpel limit is the particular case of the GEV for psi equal to 0. The viable is the particular case of the GEV for psi is negative, and Frechet limit is the particular case of the GEV when psi is positive. All right. The next slide, I talked about the PDF, or the density of the, so you just differentiate the CDF to get the PDF, right? In the next slide, I talked about the quantile function. Now talk about remember, I don't know, a quantile, if you don't know what a quantile is, defined by this equation, plus. So basically the pth quantile is defined as the probability that the random variable is less than or equal to xp equal to p, right? So if you solve this equation for the GEV, the pth quantile for the GEV distribution turns out to be this, right? Turns out to be equal to this, yeah. All right. And then the next is the return level. Return level is basically a level that is a value of the random variable that will be exceeded once in every t years. So t is an integer. It can be 10, 100, 1,000, 10,000, and so on. So to work out the t-year return level, you need to solve this equation. So the probability that the value will be exceeded is in once every t years, right? So if you solve this equation for a GEV, this is what you will get. This is the formula that you will get. This is the formula for the t-year return level. And the next thing is estimation. Excuse me. Estimation, this is the likelihood function, right? And for the GEV. And this is the log likelihood function. Yeah. And to obtain the MLEs for the three parameters, you need to solve these three equations. And it turns out that the partial derivatives are these three. Okay. So you can solve these equations 1, 2, and 3 to obtain the MLEs for mu, sigma, and psi. It's clearly complicated, but fortunately, if you're using R, I'm sure most of you are familiar with R, the software R. There's a command called FGEV. there's a command called FGEV in R that you can use to compute the MLEs of the 3 parameters. All right, so this is on the GEV. The next video I ask you guys, before I go to the next video, do you have any questions? Any questions on what I've done, talked about so far, guys? Hello, guys. Also, those guys in the video, please let me know if you have questions. Sorry, those in the Zoom, I mean. You okay?
Yeah, well, yes, sir.
Sorry. Sorry, you have a question, ma'am.
Yeah, the function R, it gives you the values for the 3 parameters, right?
Yeah.
Without doing the relative.
Yes. Yes, Veronica. Yeah.
What do you actually input into the
You just input the data on the on the extreme values under definition 1. So for example, if you have like stock data, say for the last 100 years, right, you can pick up the largest stock value in every year. So that will constitute under definition 1, that will be an extreme value, right? So for the last 100 years, you will have 100 extreme values. So that will constitute the data for the FGEV command. You know what I'm saying? So you had to pick a data that matches up with the definition 1 of extreme value, right? Remember, definition 1 says that extreme value is something which is the largest data over a long period of time. That's the definition 1, right? All right, now let's move on to definition 2, guys. In definition 2, the extreme values are defined as all values exceeding a threshold U. So the blue line is the threshold U, and all the data values that are above this line U is an extreme value, right? Now, so far we only talked about definition 1. Okay, so today I'm going to start talking about definition 2. I hope you watched this video. Now, what it says is that, all right, if X is the variable of interest and U is the threshold, then this probability, that the probability of X minus U greater than X minus U is the excess amount, and X greater than U is the event that X is an extreme value. This probability approaches this, right, as U approaches the upper end point of F, right? And this is a fundamental result in extreme value theory, and is due to James Pickens, is an American mathematician, a statistician, right? So using this result, right, you can show after some calculations, I hope you followed this, that the CDF of Y, right, is equal to given by this, and this is referred to as the generalized Perito distribution, right? So that's what I've said in the next slide. So the generalized Perito distribution is a distribution that has this as the CDF, right? There are 2 parameters, sigma and the shape parameters. Yes?
What's different about this Perito distribution and like just the normal one? Because the normal one doesn't have the probability that X is greater than U. Is it just U is a parameter?
No, U is not a parameter. U is a fixed. U is fixed number. There are only 2 parameters. There are only 2 parameters, sigma and psi, right? Good question, Robert. The difference here, this is different from the normal Perito because the domain is defined differently. For the normal Perito, usually y is greater than 0. Whereas here, the domain of y, which I will talk about in a minute, is defined, it depends on these two conditions. Yeah. Okay. So that's the next, so the domain of x again depends on the value of the shape parameter. If it is positive, then the domain is this. If it is negative, if it's negative, the domain is this. Okay, and if the domain, if psi is 0, then the domain is this. So in summary, the domain can take one of these forms depending on the shape parameters, non-negative or negative. Sorry guys. All right. So that's about the domain. And the next thing, when psi is equal to 0, when psi is equal to 0, the CDF, which is this, right, simplifies to something very simple, which is this. And you may recall this. This is a shifted exponential distribution, right? It's a shifted exponential distribution. And the next slide is this. This is just the density of the Perito distribution. Somebody pointed out a mistake. Actually, there should be a -1 here. I apologize for this. Thanks for pointing this out. There should be a, when you take the derivative of this with respect to y, you should get a -1 here. Okay. So if you haven't spotted, please correct it. Thank you. And the next slide is the quantile. Remember, the quantile is defined by this formula, and you should solve this for a generalized Perito random variable. Your quantile will be equal to this. It will be given by this, right? Okay. And the next thing is return level. Now, in this case, to get the return level, you need to solve this formula, because if you take, say, t years, capital T years, the extreme values are not like one every year, because the definition is different. In definition 1, there's only one extreme value every year. But in definition 2, anything that goes above the threshold is an extreme value. So if you have, suppose you have m is the integer, suppose you have m extremes every year. So over capital T years, you will have m times t extremes. You follow what I'm saying? M is the average number of extremes per year. So over capital T years, the number of extremes will be m times t. So in order to solve for the return level, you need to solve this equation, that the probability exceeds the t year return level is 1 over mt. Mt is the number of extremes over the t year period. I hope you follow this, guys. If you don't, please let me know. All right, now the next thing is about estimation. This is the likelihood, this is the log likelihood, and these are the two equations you need to solve. And it turns out that the partial derivatives are this and this. So to obtain the ML estimators, you need to solve equations 1 and 2, right? So in once again in R, in the R software, there's a function called fpot that you can use to compute the MLEs of sigma and psi. So fpot is similar to FGEV, except fpot applies for definition 2, whereas FGEV applies for definition 1. So to apply fpot, you need to have data, like say, you should have 10 years of data, and every year you have, say, so many extreme values. So you take all the data over the 10 years, which are extreme values, and put them as the input for fpot, right? You know what I'm saying? Yeah. Okay. Yeah. So that's definition 2, guys. The next. So let me take this away. So that's definition 2, right? Any questions so far? Before I go to the final video. Hello, guys. Talk to me. Are you okay so far, guys? You can use the chat room if you are in Zoom to ask questions, right? All right, the final video I asked you guys to watch is about definition 3. Definition 3 is the last definition I gave you. So in this case, you don't just pick the largest data point over a year or whatever. You pick the first few largest, so the R largest. In this case, R is 5, right? Okay. So now, definition 3 of extreme. So you pick the R largest data points, and it turns out that the joint, because you have more than one, you're looking at the joint distribution of the scaled versions of the R extreme values, and it approaches something very complicated like this as n approaches infinity, and this result is due to this person here, 1978, right? So this is the fundamental result for definition 3. And you should, so this is the CDF, as you can see, it's a joint CDF. Now you should differentiate this with respect to the parameters, right? This is what you will get, the PDF, the joint PDF of the R extreme values will look something like this after a lot of math, right? Now for estimation, suppose these are the extreme values for the first year, and these are the extreme values for the second year, and these are the extreme values for the 10th year. Then the likelihood function will be something like this, right? And the log likelihood will be this, and the MLEs will be the solutions of these 3 equations. Again, I have worked out the partial derivatives. So this is the partial derivative with respect to mu, with respect to sigma, with respect to psi. So you should solve these 3 equations. You will get the MLEs for. Are you guys okay? Yeah, sure. Yes.
Is the second PDF the PDF for MN, or is it for the scale one as well?
Which one you're talking about? Sorry.
This sigma for-
You mean this one here?
Yeah, is it for the scale one as well, or is it this the MN?
No, it's for the MN. MN1.
The same as the previous one, is it?
I have taken account you mean, yeah, I have actually, when I differentiated this, with respect to x1 to xr, right, I have taken account of the an and the bn. So in effect, the three parameters here, mu, sigma, and psi, they depend on an and bn. Yeah. So yeah. So this is a joint PDF of these of the R extreme values. I know it's not immediately obvious. I mean, your question is good because it's not immediately obvious how sorry, where's it? This page. How I differentiated this R times to get this, but after a lot of work and after a lot of differentiation, after you will come to this something like this, where mu, sigma, and psi are functions of an and bn. Yeah. I don't expect you to know that anyway. So, all right. So the MLAs are the solutions of these three equations, 1, 2, and 3.
Is there no R functions if you have?
There is a R function to do it also, but I can't remember. I think I can't remember the name of the function right now off the top of my head. But if you go to, there's a package called EVD, which if you just Google it online, you will know the name of the command to solve these three equations, right? Okay, guys. So that completes, I think, the 4 videos I asked you guys to watch. That completes any questions on. That completes the 4 videos. Any questions you would like to ask anybody else in the Zoom? Hello guys, talk to me. Yeah, all right. In the remaining time, what I like to do is to do some examples. So the first example I'm gonna do is suppose X is a Bernoulli I'm sure you're familiar with the Bernoulli random variable, right? Which basically means that it takes 2 values, either 1 or 0, 1 with probability P and 0 with probability 1 minus P. Now the question is, does the extremal types theorem hold? Right, the first, you may recall just a few minutes ago I told you what to do in this case. In this case, in order to check whether the extremal types theorem holds or not, right, you need to check a condition, and this is the condition that you need to check, right? This one here. And if the limit is 0, then the extremal types theorem will hold. And if it is not 0, then it will not hold, right? Okay. Now, so basically, the first thing we need to work out is W of F. W of F is the, as you can see, X can take only 2 values, 0 or 1, right? So the largest, remember, I know, like in the quiz, I know some of you actually tried to solve the equation, the CDF equal to 1. And sometimes, I mean, the quiz, it was okay, but sometimes solving that can be really hard. It can take you a lot of time, you know. So, but in that case, the best solution is to look for the value for the domain. Look at the domain of the random variable and pick the largest value. So in this case, the domain of the random variable is 0, 0 or 1, right? Okay. So what is the largest point? So the largest point must be 1, right? You follow me? So this is as k approaches 1, you don't need the limit anymore. You just, this is the probability x equal to 1. Okay. And this will be the probability x equal to 1 is p, and f at 0 is 1 minus p. Okay. So this is and this is 1, which is not. Okay. Is this clear to all of you or not? Yeah, any questions, guys? So basically you're working this out at x k equal to 1 because your w of f is 1, right? So this becomes this becomes this because of what is given to us. The probability x equal to 1 is p, and the CDF at 0 is simply the probability that x equal to 0, which is 1 minus p, right? So you have 1 minus p. It is p divided by p, which is 1, which is not equal to 0, right? Okay, guys. Next example is example 2. Right? Okay, can you, in this case, what do you think the answer will be? The question is the same, does the ETT hold, right? So the first thing you need to figure out is the W of F. Now what do you think the W of F will be? It's 1, right? Because the values that the random variable can take, sorry, it's not. Yeah, you're right, sorry. I'm being stupid again. Because it's k0. Yeah, you're right, Veronica. Because the only value that the variable can take is k0, and it's undefined everywhere else, right? So it's k0. So this is going to be the limit this is going to be the probability that x equal to k0. Right, and this guy is the probability that x equal to k0 is 1, right? And the CDF at k0 minus 1, because it's only defined at k0, the CDF at k0 minus 1 will be 0, right? So this is 1, which so ETT ETT fails to hold, right? Is that okay, guys, everybody? Any questions, guys? Please feel free to talk. Use the chat room if you're in Zoom. Right. All right. The next example. I'm not sure if I have the time. I will anyway. I'm not sure if I'll be able to finish this. Example 3. Suppose right now, I'm sure all of you know the Poisson random variable, and you will know that the probability that x equal to k is this. Yeah, this is the probability mass function of the Poisson. So if you look at, once again, if you look at the domain of the Poisson, it goes from 0, 1 to up to infinity. So it's it should be clear to you that W of f is infinity. Remember, you look at the domain and see what's the largest point of the domain. That should be the W of f, right? So in order to check this condition, you need to take the limit okay. Now this you can write as okay. Now 1 minus the probability that x is less than or equal to, this is the definition of the CDF, right? So 1 minus of this will be the probability that x is, you okay, Veronica? Yeah. This will be the probability that x is greater than or equal to k, right? And this is the limit Yeah. Okay, guys. So I have written the probability that x is greater than or equal to k as the sum of the probabilities from k to infinity. Okay. Now you see why I have done this. You will see in a minute why I'm doing this. Now this guy here we know is E of right. Okay. Now you see that this one and this one, these are constants, yeah? So you can cancel them out, right? Are you seeing this or not? Yeah. So these are constants, so you can cancel them out. And so this will become the limit at k goes to infinity of okay. Yeah. Right. I'm not sure. I think I maybe run out of time now. But what I'm trying to show you is that I want to show that this limit looks complicated, but I want to show that this limit is not equal to 0, proving that the extremal types theorem does not hold. Right? That's the purpose. Right? I mean, but you need to. This is where your mathematics comes in, really. Whatever you learned in the years before. So this will become the limit okay. Yeah. Have I run out of time? Not yet. Only 2 minutes left here. Sorry, guys. So now I think I may not have the time to finish this, but I would like you to try in your own time. I'm not going to ask this question in the exam, so don't worry. But I would like you to show that the limit that I have here is not equal to 0. Right now, J is a number that is greater than or equal to k, right? So, so k. So you can see that k could be somewhere here, right? Remember, j factorial is the product of all the numbers from 1 to j, and j is greater than or equal to k, right? So what will happen is all these numbers will cancel out with all these numbers, right? And so you will get this to be equal to something like and please, because I run out of time now, but please try to show that this is something that is, sorry, you can't say it. This is something which is not equal to 0, and that will prove that the extremal theorem fails to hold, right? It's not something I expect you to know, but if you want to try out your math skills, it's something good to practice. Yeah, okay.
Would you finish and upload that later, or should we just try and do it ourselves?
Yeah, I can fill it in and scan it and upload it to the website. Yeah, later on. I will do that later on. Okay. Yeah. Thank you, guys. Sorry for running up. See you guys. Take care.
Thank you, bye.
Bye. Hello.
Hello. How was your technology today?
Okay.
Okay?
Yeah.
That's great.
Sorry for running out of time.
It's okay. It's okay. We're good. Thank you.
Yeah.
Have a good day.
You too.
No, I'm a lecturer and just a top intern.
Okay, so you're actually we came just in case of an extra support.
Oh, wonderful. I mean, you're welcome to stay. But yeah, I think you probably had it down. Were you booked through the rota?
No. I think Ellen,
Yeah.
Ellen was booked through the rota with the TSLs. We're like extra
Oh, great.
people.
Great.
Yeah, because we weren't sure if the booking had like gone through. We
Yeah.
weren't notified, so we just
Yeah. No, thank you so much because I haven't been able to log into the internal booking system. So all of my booking requests have like not happened, and then it means that too late, which is probably what happened.
Okay.
But apparently, if I do it through incognito, they'll let me in. But they're just like, you specifically aren't allowed to book.
Okay. Well,
Okay.
you're all good then.
Yeah.
We'll see. We hope we're all good.
I know. I say that now. To be fair, we could just wait until we've got the tech rolling before you go, just in case I start crying in 5 minutes' time. In other news, I can now log on to university computers, which is really good development compared to the first 2 weeks when I had to get my students to log in for me.
The uni really just doesn't want you
I know.
getting involved.
I think it's like kind of ghosting me, but not firing me. Like it's just like, we won't call you back. We'll say if you quit.